We now return to our conservation of energy model, and we're going to move into some energy diagrams after this. So right now we still don't have all of the pieces of conservation of energy, but we can completely define conservation of energy for an isolated system. What that means is we worry about the system and we don't have to worry about anything in the environment. There are no interactions between the system and the environment. What this means is that there is no external work done. So later we will define what the situation is when that is not true. The energy of our system then stays constant. The change in the energy of our system is equal to zero. Now that means that the individual types of energy within our system may transform into one another. However, the total amount of energy is going to stay the same. That means that we can then set the sum of the change in kinetic energy plus the change in potential energy plus the change in thermal energy to be equal to zero, since transforming one into another does not change the total sum. So whenever you encounter a problem that you think is good to solve with energy, you want to use an energy conservation approach to solve it. Again, this is chapter 10 material where chapter 9 focused more on work, but since in many cases you might have a combination of different potential energies, I think it's really helpful to define it that way rather than trying to juggle work and potential energy whenever possible. So first, whenever you are dealing with conservation of energy, you must define your system. So if you have no external forces or no external forces doing work on the system, it is then isolated. Defining an isolated system is a model. There's not going to be any real-world system that is perfectly isolated, but we can approximate many systems as isolated. Now again, later we will introduce what happens when this is not true. But if you can define your system as isolated, you should, and then this is very simple. The representations that you might choose to draw include a before and after representation, so that's a type of sketch. You could also do an energy bar chart. I won't require you to do an energy bar chart, but it can be really helpful to think about all the types of energy and how they're changing. An additional type of visualization we're about to talk about is an energy diagram. Now, obviously, you might still need to do a free body diagram if there are many forces going on, but if you are primarily just dealing with energies, kinetic and potential, you don't necessarily need to do a free body diagram. So if we have an isolated system that is non-dispersive, so saying non-dispersive means that our change in thermal energy is equal to zero, then mechanical energy is conserved. Mechanical energy is the sum of our kinetic and all of our potential energies. Remember that at this point U could be gravitational potential energy, spring potential energy, or both of them. So in this case, the sum of our initial energies is equal to the sum of our final energies. If we do have friction, we now need to think about the thermal energy, and we put that on the side with final. So some of our initial energy has gone into a change in the thermal energy. We never talk purely about an initial and a final thermal energy. Since everything around us has some thermal energy, we don't necessarily know that starting value. So the way we're defining thermal energy is due to friction. So if your object is moving with respect to the surface, it must be kinetic friction, and then delta S is the length that it has traveled on that surface. I'll also use curly L sometimes. So this is the general approach. And again, it's important to recognize when you want to solve a problem using energy, there will be many problems where you can choose to use energy or you can choose to use forces and acceleration. And that's going to be largely up to you which approach you're going to want to use unless you're explicitly told, for instance, on the homework or on the test, which way you have to do it. You want to make sure, based on your choice, that you're being consistent in your models, your representation, and your calculation.